So to be sure we understand what's going on, let's do one more example with the direct test. So let's say f of x is sine of x. And we'll limit our domain to the interval from 0 to 2 pi. Then our critical values, and again, we can immediately put in the endpoints. So we have got 0 and 2 pi. So our critical points, we know that 0 and 2 pi are in there. And we need to find out, are there any others? So we look at the derivative. So f prime of x is cosine of x. And since cosine always exists, this we want to know, when is it 0? And cosine is 0 exactly when in our domain. So it's 0 a lot of places in the real numbers, but we're just looking for values between 0 and 2 pi. And so it's going to be 0 when x equals pi over 2, or x is equal to 3 pi over 2. Those are the spots where cosine is 0, so we need to add those to our set of critical values or critical points. So we've got pi over 2 and 3 pi over 2. And now we just need to evaluate our function on those critical points. So I'll make a table. We'll look at our critical points. We'll evaluate f. So we need to evaluate it at 0, at 2 pi, at pi over 2, and at 3 pi over 2. And so our function is sine. So sine of 0 is 0. Sine of 2 pi is 0. Sine of pi over 2 is 1, and sine of 3 pi over 2 is negative 1. And now we can compare which is the largest, what's our maximum value, and our maximum value occurs here. This is our max. And our minimum value is negative 1. So this is our minimum value. So it's pretty straightforward. If I want to find my max, I want to find my min, I just need to find all my critical points. And that's either using the endpoints, or where the derivative is 0, or where the derivative fails to exist. And once we have all our critical points, we can list them out, evaluate our function on those critical points, and we can find exactly the largest value is our max and the smallest value is our min. Now this requires being able to compare. What happens if we only have one critical point? So this could happen if we have an open domain, so we don't have endpoints, and so maybe we just have one place where the derivative is 0, or one place where the derivative doesn't exist. And in that scenario, we need to look at a second test called the second derivative test. And so what we start with is we've got a critical value, and it's the only interior critical value. So, and we have the derivative is 0. So what it says is that if we look at what the second derivative is, right? Here we have the first derivative is 0, but we ask, what is the second derivative at that point? And if the second derivative is negative, then you have a maximum. And if the second derivative is positive, then you have a minimum. And if the second derivative is 0, then the test is inconclusive. So at first blush, it may be unintuitive why the second derivative would give you information about the maximum or minimum. But let's look at this video to get some intuition about it. So here we have an example of a graph, and we can see we have one critical point interior. one interior critical point, and it's a maximum. So let's talk about the slope of the curve up to this point. We know at when the value when our input is 3 that we'll have a 0 slope, right? So we know the derivative is 0 there. But what about before it? So if we look before it, we've got a positive slope. So here the derivative is 0, and after it the derivative is positive. Now let's think about what the second derivative measures, right? The second derivative measures the rate of change of the slope. So what's going on here? Well, over here we have a very steep slope, but as our input gets closer and closer to 3, the derivative is getting less and less positive, right? So it's going from a very large positive value here, and as we get closer and closer, the positive values start getting smaller until we hit here, we get 0. And after that, the values of our slope will get more and more negative. So we can see that the rate of change of our slope is going from very positive to very negative. And so the rate of change of our slope must be decreasing, which means that the second derivative must be negative. In fact, all through here, the second derivative is negative. In particular, even here where the first derivative is 0, the second derivative is negative. So that's why at a maximum, the rate of change of the slope is negative, because the slope is going from extremely positive, it's decreasing, decreasing, continues to decrease, decrease, becoming more and more negative. So the second derivative is negative. Now on the other hand, let me remove this graph and look at a different function. Whoops. So we can scroll down here. So now we have a minimum value, right? We've got a minimum value here, and do the same analysis of the slope. So again, at the minimum, we know the slope is 0, right? We've got a horizontal slope, but if we look before it, it's a very negative slope. It's going downhill. So we have a negative slope, and but it's becoming less and less negative. So it's going from negative values until it gets here and it gets to be positive values. So if a function, the slope function, is going from extreme negative but getting bigger, right? Becoming less and less negative until we get 0, and then it goes to positive. And so throughout this whole curve, the rate of change of the slope is increasing, which means that the rate of change of the slope is positive all through here. And again, the rate of change of slope is the second derivative, and that's why at minimum we've got to be in some region where the derivative is increasing as we move along, which makes the second derivative positive. And so here we have a min, and the whole thing is what we'll discuss in the next section, is that the shape of the graph is what's called concave up, and that occurs when the second derivative is positive. Okay, so hopefully that helps with your intuition for the second derivative test. Let's look at an example. Let's say f of x is negative x squared plus 6x, and we'll look at the domain where x is between 0 and 6. So this is an open interval. I don't have any endpoints, so I don't have critical values associated with the endpoints because I'm not including them in my domain. So the only critical values I could have is where the derivative is 0 or doesn't exist. So f prime is equal to negative 2x plus 6. Now this exists for all real numbers in our domain, so we need to ask the question, when is it 0? And this occurs precisely when x is equal to 3. So our one and only critical value is 3. So our set of critical values is 3. Now, hopefully you can see here, I can't compare this. I can't do any comparison. So the direct test is of no use to me in this scenario. But I have the second derivative test that says, okay, we found our critical value. So we found our C, and it's C, or it's 3. Now we just need to look at the second derivative. Is it positive when we evaluate it there, or is it negative? So let me evaluate f double prime of x, which is, we've already computed the derivative, so this is the derivative with respect to x of negative 2x plus 6, which is negative 2, which is always negative. So in particular, f double prime of 3 is just equal to negative 2, which is negative, right, less than 0. And then by the second derivative test, since it's negative, that f of c, this tells me that f of 3 is a max. Well, what is f of 3? F of 3, I would put it into here, so that tells me that negative 9, which is the value of f of 3, is my max. So the second derivative test is pretty straightforward. I find my critical point, and if I only have one, then I'm good, and I can put it in and just evaluate it at the second derivative. Now, here's another warning I want to give you as a student. Common mistakes I see would be that students will take the critical value and put it into the second derivative and then say that that's the maximum, which is not the case. This is just a test. Right? We just need to know, is the second derivative positive or is the second derivative negative? Then we take that number and put it into the original function because it's the function f. F is the function we're investigating. We're just using f prime and f double prime as tools to understand the maximum value of f. These are just tools. The function that we're interested in all of this investigation is the function f itself. We're just using the derivative and second derivative in this case to find out information. Do we have a maximum or a minimum?